Pleased to have today for our colloquium Smillie from Cornell and eventually Warwick, who will talk about closed orbits on rational billiards. The colloquium will be followed by a dinner and Professor Misha about the day.
What do you mean eventually Warwick? You going to work?
Yeah. Yeah, we're both fine. So, let's start with a polygon contained in the plane, like, and I want to, for reasons I'll explain shortly, I want to think about polygons whose angles are rational multiples of pi. They could be, so here are two examples. And then inside my, I want to think of this polygon as a pool table, billiards table. So I want to consider trajectories, so straight line orbits, which bounce off the side, so that the angle of incidence is equal to the angle of reflection. Okay, so we can think of this as a dynamical system. This billiard flow, billiard systems have been studied by dynamicists for a long time, kind of classic models. But this polygonal case, though it might seem simpler than other boundaries, is actually not so simple, and it's only kind of being understood now. In fact, what I really want to do is not so much present. I want to present some results, but I want to present questions. Questions sort of how this should be studied. What's the appropriate kind of dynamics to use to study this problem? Okay, so the question, one of the things that you typically look for in dynamical systems is closed orbits. So let's look for closed billiard trajectories on these polygons. So the question is, do there exist closed orbits? And if so, how many? So we can make that sort of quantitative if we define, so if we let n sub L be the number of closed orbits of length less than equal to L, then how does n of L grow, if indeed it grows at all? But let's think about sort of the asymptotics of that function. So one observation is that if we're thinking about closed orbits on billiard tables, so here's an example of a closed orbit. Almost, well, so close. Close enough. Close, yeah. If we have a closed orbit in the polygonal situation like this, and we take something very close in parallel, we'll get another closed orbit. So closed orbits tend to come in families, that we can get parallel families. So when we count closed orbits, well, let's count the families, right? We will not the individual orbits. Okay. So in the case of triangles, we have the following theorem. So they're exists in a closed orbit on an acute triangle. Okay, 1775, when this was proved.
What's the second digit?
1775. Okay, so the construction is as follows. If you look at the altitudes of the triangle, okay, so these are lines from vertices that hit at the opposite sides, then these intersect in a single point. And if you connect the bases of the altitudes, then this will be a closed trajectory. In fact, it's also the triangle of minimum perimeter inscribed in this triangle. Okay? In fact, minimizing things is a kind of a classic technique for finding closed orbits, or variational techniques, or classic techniques for finding closed orbits. This is about the only place that variational techniques work in this entire subject. I mean, variational techniques. I mean, this is sort of the end of the story of variational techniques, 1775. After that, yeah, so that's not really what we want to be using.
So what happens if it hits the corner?
Pardon?
Well, one hits the corner.
Well, that's the problem. So in the Fagnano case, as long as I assume it's an acute triangle, it won't hit the corner. But if it becomes a right triangle, then this will kind of degenerate. And in general, that's the problem with the variational techniques, is you can't use them because when you try to minimize something, your orbits run into corners. Okay, so you put your your question is exactly the issue. Why these techniques don't work very well beyond this case. Okay, so for example, with obtuse triangles, if we drop the rationality hypothesis, it's not known whether there are any closed trajectories at all. As an aside.
Is it non-experimental? Presumably people have been drawing triangles.
It's known, well, so acute triangles means that the largest angle is bigger than 90 degrees. Obtuse. I mean, it's bigger than 90 degrees. So it's known if the biggest angle is between 90 degrees and 100 degrees through exhaustive computer search. But it's hard to extrapolate beyond that. Okay, so the techniques.
Rigorous results.
That's a rigorous result, but it's not. It doesn't suggest exactly. It's wrong to assume that 101 degrees is going to be easy just because it works up to 100 degrees.
So this is Schwartz?
Yeah.
So this isn't.
Rich Schwartz and Pat Hooper. So it's but it's intensive computer calculation with rigorous computer use. So if we're not going to use variational techniques, we need to somehow exploit these rationality properties of our triangles, so our polygons in general. If we start with, say, a square, and we consider a trajectory in the square, we can unfold the square and straighten out the trajectory. So each unfolded version, so this initial trajectory in the square, every trajectory travels in, or trajectory vector travels in most 4 directions. So each of these copies somehow corresponds to one of those directions of travel. If we continue through here, we get a new square, but this corresponds to the original direction of travel. So we can identify this, so this square corresponds with that square, same direction of travel, so that we can, instead of adding on a new square, we can just identify sides like that and create lift our billiard trajectory up into a geodesic of the torus. Okay, so, but that's maybe that suggests that things are a little simpler than they are necessarily. If we start with this example.
So that problem is done now.
Yeah, well, we've got existence. We've got existence. I'll say a few more words about the exact asymptotics, but we have existence definitely. So it's, since we can unfold this to the plane, then we can think about these trajectories as sort of corresponding to lattice points. Right? And, well, let me compare here with this. This other triangle. If we do the same operation with this triangle, so in this case, we have a trajectory can travel in 8 directions. So if we unfold this 8 times, we get an octagon, and if we make the appropriate identifications, we are identifying sides. We're identifying parallel sides. Okay, so in this case, we get a surface of genus 2 rather than a torus, rather than a surface of genus 1, and this vertex, if we glue these vertices glued together to form a single point in our surface, and at that point we have a cone angle 6 pi. Okay, so we've got a singularity in the structure here. So.
And flat everywhere else.
Flat everywhere else. Not only it's flat, and it's got a well-defined notion of parallel translation everywhere else. Right. So it's there's a well-defined. There's a well-defined directional flow on the surface, and it's flat outside of this point. Right. So you can think of this point as either having cone angle 6 pi or curvature 2 pi minus 6 pi equals minus 4 pi. So it's satisfies Gauss-Bonnet, but all the curvature is associated, is concentrated in a single point. Okay. So this is an example of a translation surface. So the flat structure can be described by saying it's got a collection of coordinate charts where the overlap functions, the coordinate charts in R2, where the overlap functions have the form P goes to P xy goes to xy plus a constant. Okay, and singular. So it charts everywhere outside of the singular point. Okay, so translation surfaces come up in other contexts besides.
The overlap map is a translation. So
Pardon?
the overlap map is a translation.
The overlap map is a translation, yeah. So these translation surfaces arise in other contexts besides polygonal billiards. So let me mention two of those. So translation surfaces arise in connection with integration of holomorphic functions, integrals of f of z dz, say on a complex plane, where f is a holomorphic function, away from the zeros of this holomorphic function, local antiderivatives exist. So, and those local antiderivatives give us charts on our domain. So we have charts, and the fact that two antiderivatives differ by a constant means again that those charts fit together by, so z goes to z plus c. So
Well, f is like not single value. You're assuming.
Pardon?
F is like not single value.
Well, it could be single valued, or it could be not single valued. It could be some cover of. I mean, so for example,
I don't see why you had any problem. You said zeros of f.
let me give you two examples. Well, so at the zero, so if f is non-zero, we get a translation structure. At the zeros of f, we get cone-type singularities. So we're getting the same kind of picture as over there. So, for example, integral dz over z, the translation surface picture of this is just an infinite cylinder. Right? Looks like a, or integral.
So there's poles of f of z, not zeros.
Well, let me throw out the pole. Okay, I'll make it whole. So let's make our domain c minus 0. So there are no singular points in that one. But we could also consider this one. So in this case, we could think of this as a two-value function over the complex plane. In which case, and we can add a point at infinity, in which case what we get is just a torus again. It's an example of elliptic integral. Okay, so that's one place where translation surfaces arise. So let's see, why am I mentioning other places where translation surfaces arise? Because it doesn't quite seem like real math to start with here, so I'm trying to solidify my credentials. You know, so I should say here, the code.
Okay.
Am I good? Okay.
Now, which triangles lead to translation surfaces? What about three?
All rational triangles lead to translations.
Oh, it is?
Yeah, all rational triangles.
Wow.
You have to draw them. And, so all rational polygons lead to translation surfaces. Not all translation surfaces come from polygons.
The issue is that they go as you reflect around, they don't fit.
No, the rationality condition here means that I can build out of a finite number of these triangles. I can build my surface.
So you can lay on a blackboard and glue sides together. I mean, it covers itself.
Yeah, that's right. That's right. So I can't always draw this picture,
right.
But I can always
fit triangles together.
Yeah, maybe I'll make a bunch of triangles and just a complicated gluing pattern between. I may not have So they're all good from that point of view. Let's say the other place that translation surfaces arise is, let's see, so Thurston's theory of diffeomorphisms of surfaces. So Thurston was, for various reasons, wanted to construct a theory of diffeomorphisms of surfaces, and I think he was inspired by the beautiful situation in the case of the torus. In the case of the torus, every diffeomorphism is isotopic to a linear map of the torus. So that's that gives you a very nice model which is easily understood. In general, if you have a surface of higher genus, well, if you have a translation surface, there's some analog of a linear map, which would be an affine diffeomorphism. So let me say definition. An affine, let's say, or autumn diffeo of a translation surface is a differentiable map. The differentiable homeomorphism, say, away from the singularities with constant derivative. Okay, so in general, constant derivative doesn't make sense, but if we have charts in R2, we can think of the derivative of the map as a 2x2 matrix, so it's an element of SL2R, so it makes sense to be constant. Okay, so in Thurston's theory of surface diffeomorphisms, the fundamental building blocks are affine automorphisms of translation surfaces. These give rise to pseudo-Nassau maps, and every diffeomorphism could be built out of pseudo-Nassau pieces.
That theory does he need to use also quadratic differentials, not only linear differentials?
Yeah, so quadratic differentials too. So I lied a little bit.
Not quite translation surfaces, a little bit broader class, yeah?
Yeah. So if we look at, if we go back to this example and don't actually pass with a double cover, then we would get something like this, where we have a flat structure, but we don't have precisely well-defined translation. We might come around and flip our direction. Okay, so this would correspond to a quadratic differential, and he uses those. I mean, to be honest, we would use those.
You could take a little bit of coverage space here and make it a translation.
Yeah, but that's not really fair. If you want to understand a particular map of a surface, you want to stick with that surface. And you don't know a priori what the translation structure is going to be. So we would really want to extend the theory a little bit, but okay. Okay, so let me return, just because the torus is an example that we can analyze very concretely, let me look at the second question about the number of closed orbits in the case of the torus. I want to say that the situation for torus is going to work out something like this situation. I mean, this situation for this surface is going to work out something like the situation for torus. But let me start by reminding you what the situation is for the torus. Okay, so just erasing the definition of N of L, which is what I want to calculate here. Okay, so as Dennis was pointing out, in the case of the torus, we can identify, if we keep unfolding and pass to the universal cover, we can identify closed trajectories with lattice points of the plane. not all lattice points. This lattice point, after all, corresponds to doing this loop twice. So we would rule out that lattice point, rule out that lattice point, rule out that lattice point. So the lattice points we want to consider are those P, Q, which are relatively prime.
You can see that in the origin.
They're visible from the origin, right? We're not getting anything that's hiding behind something else. So if we want to calculate n of L, well, that's going to be approximately n of L is approximately pi L squared times the probability that a given pair of integers is relatively prime. Right. So let me call that delta. So if we want to calculate delta here, well, so delta is, say, the density of these relatively prime guys. But how do we calculate delta? So if you take the relatively prime ones, that's some subset of everybody, all the lattice things, and then you multiply it by 2, you get something of density 1/4 delta, and you multiply it by 3, you get something of density 1/9 delta, right? And if you look at all those multiples, you get everything. So we see that delta plus delta over 2 squared plus delta over 3 squared plus delta over 4 squared plus is equal to 1. So that delta times, so 1 plus 1 over 2 squared, etc. is zeta of 2 is equal to 1, so delta is equal to 1 over zeta of 2. So we're getting a well-defined constant here. In the case of the torus. Okay, so I was saying I wanted to do something similar in the case.
What's wrong with that algorithm? Anything wrong with the algorithm? Didn't seem right. I mean, felt too good.
I'm not going to tell you what's wrong with my arguments. What I'm presenting here is a tissue of lies, and I really don't want to expose that and pull it apart. Yeah.
So if you have an orbit of length L, do you also count it as an orbit of length 2L if you just go twice around that?
No, I want. Okay. No, I'm just looking at simple orbits. Okay, so let me give you a different way of counting the trajectories on the torus. Okay, so this one's hard to generalize because I really use the fact that when I unfold it, I get the plane. But let me give you an alternative approach to the same problem. Okay, so if I'm in the torus, it's not radically different, and I have some very long trajectory. Look, but I want to give an alternative approach that's sort of just dealing with the torus as a translation surface without passing to its universal cover. Okay, if I have a very long trajectory, then by applying appropriate shears and rotations, I can reduce the length of that trajectory. Okay, this is basically, it's the Euclidean algorithm, right? So there's some sequence of shears and reflections that take my long trajectory and bring it and turn it into like a standard model. Right. So what I'm using is affine automorphisms of the torus. Right. So instead of thinking about a question of sort of counting trajectories, I can think of this as a kind of a question of counting elements of the affine group of the torus on some level, because I take any long trajectory, I associate a certain affine automorphism, and then I want to look at all those affine automorphisms that do a certain amount of stretch. Okay, so if we think about the affine automorphisms of the torus, what is it? You can draw them. There's a kind of fairy tree picture. So what I want to do is count the number of lattice points inside of an appropriately sized ball in the plane. So this is another way of approaching sort of the asymptotics of the number of trajectories. Okay, so what I will get is on the order, it's a constant times L squared, but in this case the constant is just, it's like this problem here. If we were going to count all lattice points, we would just sort of look at the area of the sphere and divide by the area of the fundamental domain, right? Which is 1 here. In this case, again, if we just think about sort of the area of the appropriate disk and divide by the covolume, so the covolume of SL, or say, divide by the volume of SL.
That's the picture of SL2R, you might want SL2R.
This is this is the what I'm trying to draw here is the sort of the fairy picture inside the hyperbolic plane, which I'm thinking about as the image of a point under SL2Z. Okay, and I'm looking at what I'm counting is the number of points inside a large ball. And what you get, again, is you get a different expression for the growth.
Shouldn't that L squared be e to the L?
Well, there's an e to the L and there's an e to the L over 2.
Yeah, but we have L squared.
No, well, so we know what the answer is. The answer is L squared times some times a constant. Indeed, the answer is, L squared. I want you to trust me on the L squared.
I trust you.
Okay. And I want to direct your attention to the constant here, which is just the covolume of SL2Z and SL2R. It's sort of that gives you sort of the density of lattice points. Okay? So, so in fact it gives it another expression. It gives another expression for zeta 2. You can calculate this covolume by looking at the volume of a fundamental domain, and you can see that zeta over 2 is pi squared over 6. No, you get pi using Gauss-Bonnet, you get pi squared over 6. So you get an evaluation of zeta 2. So you don't get, it's not zeta 2 that comes up naturally, it's the rational. Okay, so the advantage of this second approach is that, the disadvantage of the second approach is it requires a little more technical work to make it work out. In the Euclidean plane, isoparametric inequality means that the area of the boundary, the length of the boundary is growing more. The area of a neighborhood of the boundary is smaller than the area of the disk. In this hyperbolic setting, the area of a neighborhood of the boundary is comparable to the area of the disk. So a little extra ingredients need to be applied here to make this argument actually work. like including mixing of the geodesic flow, and you need to know that circles are becoming equidistributed, etc. But the advantage of this second type of argument is it works for the in the octagon setting. So. So Veach showed, what's important here is that this SL2R modulo the affine automorphism group should have finite volume, right? That's critical for this to work. So Veach showed that the affine automorphism group of the regular octagon has finite co-volume in SL2R. So this is, you can think of this, this is kind of an opposite problem to what Thurston was dealing with. Thurston said, well, give me a map, I'll find a translation structure for which that map is an affine automorphism. In this case, we've got a translation structure, and we're looking at the collection of all maps which are affine automorphisms of this translation structure. Okay, so maybe I should show you one here to make this believable. Well, first of all, they're the dihedral group acts on the octagon. So, but in addition, if we there's a shear of the octagon. So if you cut the octagon like that, you get a cylinder here. And if you re-glue this upper piece to the lower piece, you get a cylinder there. And the heights and widths of these cylinders work out so that if you do a Dane twist in this bottom cylinder and 2 Dane twists in the top cylinder, they fit together to give you an affine automorphism with constant derivative. Okay, so it's easy to construct affine automorphisms of cylinders.
Which group you existed?
Pardon? Well, so I've got so this piece here gives me a cylinder. Okay, and these 2 pieces down here, this gets identified with that. These give me a cylinder. And the modulus of this cylinder is exactly twice or half the modulus of this cylinder, so that this, okay, so, so if you put that shear together with these isometries, it generated a group of cofinite volume in SL2R, and that allows you to calculate the constant as Veach did and shows it and I did, in fact, I looked at the tape, I looked at this constant, but somehow I didn't make it into my notes. But Veach calculated this constant in the case of the octagon.
Did it come down in terms of a decimal or in terms of something?
No, it's a rational number times pi. Just like in this other case. Okay. Well, okay, so that's a small number of examples. So the collection of surfaces in order for a surface to have this beach property, amazing things have to work out for the surface. So this is an interesting case, but it's not a general case. So the question is what to do more generally, and well, so there's a theorem of Phasor that any translation surface has a closed geodesic. In fact, in an L is asymptotically between C1, is that C1 L squared is equal to C2 L. Okay, so I was thinking that I would explain how that proof goes. Remus and Maluga I think gave this proof in a seminar. So, oh, really? Okay.
I look at all those shapes.
You talk? Oh, L-shaped tables. Okay. Okay. So let me give you an indication of how this works, right? So so we don't have a group of affine automorphisms to work with, but we can still use affine deformations of our translation surface. Okay. So if we start with the translation surface and view it as a collection of polygons with gluings, and we let A be an element of SL to R, then we can apply this matrix A to our collection of polygons, and we get a new collection of polygons where edges that were parallel before are still parallel. So we get a new translation surface. Okay, so if we started with a translation surface, applied A, and got the same translation surface back, then we would be inducing an affine automorphism. But we can apply A, in any case, we get some new translation surface. Okay, so
these closed geodesics can cross themselves, right?
no, they can't cross themselves because we have a well-defined notion of parallel, of what needs to be parallel. So they're all simple closed curves. They're simple closed curves, they're not going through the singular points.
It's like there's a Connie's estimate for closed curves. And then a closed curve are like L squared.
Well, in the surface.
The geodesics in a hyperbolic surface that are embedded are also satisfied as
So generally they're going polynomially, I think, right?
Oh, right, so higher degree, right?
Higher degree. And in this case, it turned out to be squared. So not this is again the failure of any kind of variational technique. You can't start with a simple closed curve and pull it tight. Typically that won't work because you're getting a smaller growth rate for geodesics. Okay, so what's the advantage of this operation one point is that it takes closed geodesics to closed geodesics, right? As we used before. I mean, the fact that it's an affine map, it's preserving closed geodesics, it may be radically changing the length of the geodesics. But if we can find a closed geodesic for some affinely equivalent surface, then we've got a closed geodesic for original surface. Okay, so what we need is a method of recognizing closed geodesics, and so following. So if M is a translation service of area 1 with large diameter, then M has a cylinder, so a long cylinder. I mean, the reason the translation surface of area 1 has large diameter is because it has a very long cylinder. Okay, so that's my claim. Okay. So why is that the case? Well, if you have a surface of large diameter, there's some point which is far from any singular point. You've only got a finite number of singular points, so there's some point far away. So
that's a variation for us, right there.
Not give it up yet. Not giving it yet.
Take the maximum point, which is further.
No, but that's not how I'm not using that yet. I'm not using that to find the closed geodesic. So there's some large immersed disk. But if you have a large immersed disk in a small surface, that immersed disk cannot be embedded. So that immersed disk is actually wrapping around itself, creating a cylinder. Okay, so that's the technique. So then the idea here is to take our surface. We know that the problem is topological complexity and all these singular points. So the idea is to take our surface and apply affine deformations to make it simpler. So if we've got our surface, say, with two singular points, let's apply an affine deformation which brings those singular points very close to one another. Okay? And now, either we have a surface of large diameter, or there's some other segment of moderate length that we can shrink by applying an affine deformation. Well, maybe in shrinking that second one, we move the first guys far apart. But if we brought the first guys amazingly close to each other, then even shrinking the second one would leave the first segment short. So if we keep doing this, we can shorten enough segments in the surface. So the surface has a triangulation where all edges have length less than 1,000. But the surface had area 1, so that's impossible. So it means at some point in this operation, we must actually be producing something of large diameter. That's the argument.
What was that about triangles? You have a lot of triangles?
So we have a fixed number of triangles, because the number of triangles is determined by the total cone angle of the surface. So we know the number of triangles, we know the edges.
Each triangle,
we know the number of edges.
points?
Pardon? And these are triangles between critical points. We know the number of triangles, we know the number of edges. We keep shortening, we have an operation, we keep shortening edges. As long as we know that we have bounded diameter, we can keep shortening edges. And we can shorten edges until there's no edges left to shorten. In other words, until we have a surface where all the edges have small or short.
The whole thing is small.
Yeah, so that's a contradiction. So it means that at some point, we must have had large diameter. We must have had a closed geodesic. Okay, so that's
when the disk folds up, you get a closed geodesic. By the cylinder.
When you have a cylinder, that waist curve is a closed geodesic. Okay, so that's a method of finding closed geodesics. Okay, so in general, we can. Okay, so this method can be used to prove this, but it doesn't calculate the constants. Okay, so if we want to calculate the constants we need to sort of go back to this applications of some kind of, well,
Is it clear that it's L squared?
pardon?
Is it clear from this method that it is L squared rules? L squared.
Yeah, well, so what I just described says if you start with any point in the disk, then you can go a bounded distance to find a geodesic of length 1. So you can kind of cover, so the disk, the hyperbolic plane is covered by four disks. So this shows that it's at least quadratic, and the different argument shows it's most quadratic. So the general situation is, to deal with the general situation. So the general situation is not known. It's not known what the constant is, but there's a paradigm, a suggested paradigm for solving the general situation. And as this argument suggests, it deals with SL2R actions. Okay, so what you're looking at is somehow, what you want to understand is somehow the ergodic theory of SL2R actions. Okay, so it's the ergodic, so associated translation surface, they're natural moduli spaces. And what we're trying to understand is the ergodic theory of the SL2R actions on these moduli spaces. Now, if the moduli spaces were and what we would like to know is that these orbits, these orbits sort of have well-defined volume, and then the volumes of those orbits should give us the constants, sort of as in this argument here. So what we want to know is that the orbits, in particular, are nice submanifolds in this moduli space with well-defined volumes.
Is SL2R orbits close up to finite volume?
Pardon?
Is SL2R orbits?
Not in general. Not in general. In general, the SL2R, you've got a higher dimensional space, you've got an ergodic SL2R action on the space. So typically, the orbits will fill up the
right, but the ones
moduli
with
space.
exact angles, so you're saying they might be finite volume? Well, you just said something was finite.
Yeah. So this moduli space is an affine manifold. And what we would like to know is that these orbits are nice affine submanifolds with a good notion of volume, and that would be true.
A volume element.
A volume element.
But they're not finite volume.
No, they would be finite volume. And that finite volume would be an ingredient in calculating this constant C. Okay. If these moduli spaces are actually homogeneous spaces, then this would follow from theorems of Margulis and Ratner and Stony, etc. So that theory tells you that SL2R actions are always beautiful submanifolds. And in fact, so that Ratner theory does not hold in this case.
Very output to prove that.
Yeah. Well, okay, so they proved, in fact, that the SL2R orbits are nice submanifolds. In order for this paradigm to work, we should identify those submanifolds. And we also need to know that we need to know a little bit more about sort of conjectured Ratner, Margulis, Stony theory. It's politically wrong just to say Ratner theory. In fact, it should not only be true that the SL2R action should be nice, but the horocycle action should be nice. Because this will tell us that circles fill up in a nice way. So, what I'd like to, so this is a positive result, saying that good things happen. Together with Barak Weiss, we were considering horocycle. So the horocycle flow. So that's just a sub flow in this SL2R action. We're looking at ergodic invariant measures for the horocycle flow, And what we show is there are ergodic invariant measures which are supported on subsets which are manifolds of boundary. Okay, so that doesn't happen in the classic homogeneous setting.
What? Inside? What?
Let me finish this now. With infinitely generated monomers.
Oh, manifolds.
Okay, so what we do is we show that, and so Eskin and Berzicani say that the SL2R actions are nice. We say that the horocycle actions could use some work. So that there are things that definitely, I mean, they show that the situation for SL2R actions is parallel to homogeneous case. We show that there's some things that happen in this setting for the horocycle actions which do not happen ever in the homogeneous case, including these sub-manifolds with boundary with infinitely generated fundamental group. Also, there are things which are not locally linear in this setting. So this doesn't mean that the Ratner theory, Margulis-Dunny theory doesn't work. It just means it's more interesting in this non-homogeneous case than in the homogeneous case. I'll stop there.
Any further questions?
Why is it L squared? Not L to the bigger power. I mean, in other words, you only. Wait first. Are these closed geodesics? Can they be homotopic? The different ones?
Not
They're be in families then.
Yeah, no, they're not homotopic.
Okay, so we distinct homotopic class.
I mean, if you remove the singular points right there, they're not homotopic. So they're distinct.
If you remove the
classes.
single points.
Yeah. And why is it L squared? Well, I mean, L squared is sort of what you get if the horodiscs kind of uniformly cover the hyperbolic plane. So if you can't get too many, well, so that's why it's L squared.
And if we're picking out L squared simple elements from the algebra, whatever you said about the higher power.
Yeah.
So the translation sort of picks out this special
Right.
distinguished family.
Right.
So can you say one minute preview of what you did with tomorrow?
Well, I was going
What is those?
to preview what I was doing tomorrow. I was going to talk a little bit more about this kind of thing. So I'll say a little bit more about how things work in the homogeneous case, and I'll answer some. I'll be a little bit more honest on some of the questions that Dennis was asking today. But so I'll say a little bit more about
I kind of forgot how you got into this. I mean, in the octagon case, you said this concept came out to be this volume of the homogeneous space.
Yeah.
How did you follow that? And then you said that's the general argument. Okay. I should understand the octagon case and then general argument.
No, I was hoping you'd just trust me with the octagon case, but no, I mean I'm trying. Maybe I kind of over compress because there's a number of things going on here. So these orbit closures. There's various things that these orbit closures can be. But the idea is that they, in some philosophical sense, they could be analyzed the way the octagon can be analyzed. Okay, but not a literal, not exactly a literal sense. But, I mean, in the sense that, I mean, what was it, I mean, when I was waving my hands over here, what I was suggesting is that what you need to be thinking about is somehow the ergodic theory of these SL2R actions and behavior of circles. And that's the key thing. Sort of, it comes down to the ergodic theory of this SL2R action. But in order for this to produce actual constants that you can deal with, these things should be nice. So, yeah, I guess I'll just be a little more honest about.
So they use the more dynamics, so you're okay with.
I mean, yeah, a little bit more about the ergodic theory and the connection, and then explain a little bit about what's known about SL2R orbits and Hall cycle, invariant metrics for SL2R and for Hall cycles.
Is there a theory of translation streetfolds?
Translation streetfold.
This is surfaces, so is there a three-dimensional case?
No. So I think, one thing that's somewhat special here is if you're going to kind of literally extend this notion of translation structures, you probably co-dimension two singularities. So you get kind of a more, but that would make the singular set maybe a little bit more rigid if it was some kind of graph inside your object. So I think these kind of transformation techniques, group action kind of things. I mean, I think that the theory would have a slightly different character.
Any further questions? Not the thing.